Welcome to Day 10, 3.6, a summary of curve sketching. Before we get into actually graphing or sketching, let's just take a look and get some practice with the quotient rule. Okay, so a quick warm-up. I want you to try first, see if you can do this all on your own. So I'm going to kind of zoom in here. All right. If we have h of x equals f divided by g, and we're given all of this information, go ahead and find h prime of 1. So go ahead and see if you can do it. Pause the video, and we'll go from there. Okay, so if you needed that reminder of our quotient rule, here it is off to the side. I think of it as low d high minus high d low all over low low, but everyone's got their song. So now we just have to plug in, okay, and we're given all of this information, and we do our substitution, we clean everything up, and when all is said and done, we get our final answer of h prime of 1 equals the opposite of b squared plus a squared all over b squared. Okay, so now we're going to get into curve sketching. All right, so we'll definitely practice some more in class. So if you're feeling overwhelmed, we'll get there, okay? But first, here's just some summary, all right? It's a function, we can factor it, and we need to talk about the factored and expanded form. We're going to talk domain and range, the vertical and horizontal asymptotes. We need to talk about our intercepts. We'll need to talk about the extrema using that first derivative. And we'll have to talk about inflection points and concavity with the second derivative. Okay, so if we're going to analyze and sketch the graph of y equals x cubed minus 8, we'll label all of the important information. So let's go ahead and get started. Okay, so first of all, we can't really clean this up any further. We could certainly factor that numerator out if we wanted to, but nothing's going to cancel. So we only have a vertical asymptote of x equals 0. We have a slant asymptote. So remember, to find the asymptote here is we're going to compare the degrees of the numerator and the denominator. Since the numerator is bigger, we have to do our long division. So we go through the long division. X cubed divided by x squared is x, and then we're left with some remainder. I don't care about this part, so our slant asymptote is y equals x. Our intercepts, we only have when y is 0, so we get 2, 0 for our x-intercept. There is no y-intercept because we've got a vertical asymptote at x equals 0. All right, so now on to the calculus. So we need to find our first derivative. So we go through, remember that quotient rule, that's why we practiced it above. So as you go through and you clean things up, we get our first derivative to be x cubed, that should be x cubed plus 16 over x cubed. So we have a critical number when our numerator equals 0, so we'll get negative cube root of 16. And when our denominator equals 0 is when our function's undefined, so that's where the other critical number comes from. Now remember, this is a vertical asymptote, so we don't need to worry about that with the first derivative test or the second derivative test. So now we go to our second derivative, and again, our quotient rule, okay? And when everything is all said and done and cleaned up, now it does help to practice this on your own to make sure you do get negative 48 over x to the 4th. One thing we should be able to note is that this will always be negative. No matter what I'm squaring, it will be positive, and the negative over positive, our second derivative will always be negative, so we can make the conclusion that will always be concave down. Now, a possible point of inflection is x equals 0 because the denominator is 0. That would be where our function's undefined. Okay, now since we're always concave down, we know we have no point of inflection. Okay, now we can use the second derivative test because our second derivative was easily found. So now what we need to do is we need to plug our critical number of negative cube root of 16 into our second derivative. Okay, now we know that it's going to be negative because we already talked about that. So to apply the second derivative test, we take the critical number that we found, we plug it into the second derivative. This is going to be less than 0. So since it's less than 0, we know we have a relative maximum at x equals negative cube root of 16. Now, if we were to plug this into our calculator, it's about negative 2.51. And then if we were to plug this into our original function, we would get that as our y value. So we need to take that into account when we're graphing. Okay? So now we've got all of our information. We've got the pre-calculus knowledge, all the green. We've got the blue, our calculus knowledge. And now we're ready to go ahead and plot. Okay, so we go ahead, we draw in our vertical asymptote. We draw in our slant asymptote. We plot any points that we have. So we have the point 2, 0. We plot that. We've got our relative maximum at negative 2.51, etc., and negative 3.77. And we know we are concave down the entire time because our second derivative is negative. So now we can go ahead and draw in our branches. Okay, let's move on to this next example. So if our function is f of x equals 3 times x minus 1 to the 2/3 minus x minus 1. The first thing I'm going to do is I'm going to clean up f of x. So I just factored out x minus 1 to the 2/3, and we're left with 3 minus x minus 1 to the 1/3 inside. This is just going to help when we start finding derivatives and all that stuff. Okay? So now we can go through to our pre-calculus stuff. So we can talk about our intercepts. When x is 0, or sorry, when y is 0, what do we get for x? So we can set the entire thing equal to 0. This piece equals 0, that's where we get 1, 0. And when this piece equals 0, we get 28 for x. Plugging 0 in for x is where we get our y-intercept. There is no vertical asymptote. Okay, this isn't a rational function, but we do have a slant asymptote. And what we can do here is we can look at the highest x power, which is going to be negative x to the 1. So that's where we get y equals negative x from. Now we move on to our calculus. So we take the first derivative, okay, and to get our critical numbers, we set it equal to 0. And we solve. Well, when we set this equal to 0, okay, we have to solve this portion here. And really, since we're raising this to a negative 1/3, that's going to be undefined when x equals 1, and the function equals 0 when x equals 9. So we get two critical numbers, okay? I'm going to move on to find the second derivative. So when we find the second derivative and kind of clean things up, we're going to get negative 2 over 3 times x minus 1 to the 4/3. It's only undefined at x equals 1, okay? Another thing we can note about this second derivative, I'm going to jump to talking about the concavity down here, okay? Our second derivative is always negative again. We have a negative numerator. Anything taking the cube root and then raising it to the 4th power, this denominator will always be positive. Therefore, our second derivative is always negative, and we're concave down then. So that also means we don't have any point of inflection, okay? So now since we were able to easily find our second derivative, and we know it's always negative, we can test our critical numbers. However, when we test x equals 1, our second derivative doesn't exist. So we can't use the second derivative test here. We have to jump to the first derivative test for when x equals 1. And when we do that, we'll see that our first derivative changes signs from negative to positive. So f is decreasing to increasing. And so we know we have a relative minimum at x equals 1. Okay? And you should be able to see when x equals 1, plugging that into our function, we get y equals 0 here. Okay, so now taking into account the second critical number of 9, we can use the second derivative test. So plug this critical number into our second derivative, and it is negative. Therefore, we have a relative maximum at x equals 9. And when we plug 9 into our original function, we'll get a y value of 4. So now we're ready to go ahead. We're ready to graph. We can plot our intercepts. We've got 3, no vertical asymptote, and a slant asymptote of y equals negative 6. We know we have a relative minimum at the point 1, 0, and a relative maximum at 9, 4. So when we go ahead and we plot all of that information, we're going to get a graph that looks like that. These next two examples take a little bit more thought because these are just rough sketches of possible f functions and f double primes. Okay, so we are given our derivative. Okay, so we have to break it up. I broke up my derivative in terms of the sign of my derivative. Okay, so what's happening here? So my derivative changes from negative to positive at x equals 0. So I drew this dashed line to help break up the graph. It also changes from positive to negative around x equals 9. So I drew another vertical blue line here. So I then talked about it. So f prime goes from negative to positive to negative. So I know I'm going to have a minimum for f at x equals 0 and a minimum, sorry, that should say maximum. Let's change that. This should be a maximum at around x equals 9 here. Okay, so I go ahead and I plotted just a point along this line. I know this has to be a minimum, and I know this is going to be a maximum at some point. I'm not drawing in yet. Now I need to take a look at, is f prime increasing or decreasing? And what I notice is f prime changes from increasing to decreasing at this point here, which is close to where x equals 4. My vertical line is a little off. Okay, so I know I have a point of inflection here. Since f prime is increasing, I know f double prime is positive here, and f double prime is negative after x equals 4. Okay, because f prime is decreasing. Okay, so what does that mean? So it means I'm going to have a point of inflection for f. Okay, so now I'm ready to plot f. I know I have a minimum along the line x equals 0. I know I have a maximum along the line x equals about 9. And I know I have a point of inflection right here. So now we can go ahead and we know we're concave down here, and we're concave up here and concave down to the right. So now we can go ahead and draw our curve in. So f is that pink function there, and again, it's not completely accurate, but it's a rough sketch including the important pieces: minimum, point of inflection, maximum. Now let's talk about f double prime. How are we going to graph this? Well, again, what we should notice is f prime goes from increasing to decreasing. So when f prime is increasing, that means f double prime is positive, and when f prime is decreasing, f double prime is negative. So we know we're going to have a linear function here, and I'm going to change from positive to negative along this vertical line. So we just have a line for f double prime here. Okay? This is really tough to do. We will get more practice in class with these, so don't worry about that. I do want you to try this next example on your own. Look at f prime, talk about where it goes from maybe positive to negative, then increasing to decreasing, and see if you can identify if there's any minimums or maximums or points of inflection, and give it a whirl. Okay, so again, I broke it up, and now it's kind of difficult to see with all these other lines going on. But what you should have had was f double prime is going to equal 0 from negative infinity to negative 1, okay? Because f is constant here. So what's the derivative of a constant? 0, okay? Then f is linear here. Sorry, f prime is linear from negative 1 to positive 1 with a slope of 2. So I know that f double prime is going to be a constant at 2, okay, from -1 to +1. And then again, since f prime is a constant here from 1 to infinity, I know f double prime will be 0. So that takes care of f double prime, but let's talk about what f is going to look like. Well, again, since f prime is positive here, I know f is going to be increasing on this interval, okay? F prime goes from negative to positive at x equals 0. So that means f is going to go from decreasing to increasing along this interval. So if we take a look, we are decreasing and then we're increasing, okay? We also know f double prime is positive, so we're concave up here. All right, and then we take a look, okay, we have f prime is positive again, so that means f is going to be increasing along this interval. So we'll go over any questions you have next time we see each other.